Okay. So we're going to look at equilibrium for a minute. Not really going to go any further than GCSE, but having said that, GCSE equilibrium is one of the harder things you do in the GCSE chemistry. So I'm not expecting you all to have perfect knowledge, far from it. But I'm not going to go any further than GCSE today. Okay. So first of all, what do I need to have, or what do I need to happen in order to create a system in a state of equilibrium? What kind of stuff do I need? Can you just give me one answer? There's a list of them. I need a reversible reaction. So how do I write a reversible reaction? I love it when people just draw in the air. That's brilliant. So let's just use A and B for the moment. So we have that reversible arrow, the backwardsy forwardsy arrow, showing that A can go to B, but B can also go back to being A. Okay. Thank you. What else do we need?
Does it have to be done in like a closed system?
In a closed system. Okay. What is a closed system?
So there's, like, for instance, you covered where there's no external gas to like change the heat or anything.
Okay, so we don't want to change the temperature
From the external noise into there.
Well, our system is going to be...
Yeah, like we want to keep it like we can monitor it ourselves, so it's not affected by changes to like the temperature outside here.
Okay, so we imagine we've got our equilibrium in a box, whatever it is. So what would we say about the conditions inside that box?
Constant pressure.
Constant pressure, yeah, definitely. Constant temperature, yeah. Anything else? That's it. So nothing can get in or out. We imagine this sealed container where nothing can get in or out, which is kind of an imaginary idea. It's impossible to have a container that energy can't escape from. Although, actually, a polystyrene cup does a pretty good job, especially if you put a lid on it. In fact, sometimes a closed system just needs to be a test tube because the energy doesn't affect the equilibrium that much, and the chemicals can't get out because they're in a solution. So it's kind of an imaginary thing, a closed system. Nothing can get in or out, no energy and no substances. But actually, in reality, it's not that hard to create a closed system. But that's the idea of a closed system. Nothing can get in or out, energy and particles. Okay. We're doing well. What else do I need? Let's imagine I've got my reaction. I've got A and B in a sealed box and it's a closed system and it's all running nicely. What do I need for it to reach equilibrium?
The forward rate of reaction is equal to the backward rate of reaction.
All right, that's pretty important. So when we start our reaction, we'll have lots of A. To use a slightly more scientific term, we'll have a high concentration of A. High concentration means high rate, so A will react a lot, make lots of B. But as it goes on, the concentration of A will go down, the rate of A reacting will go down, the rate of the forwards reaction will go down. B will slowly increase in concentration, so B will get faster, and sooner or later they'll reach equilibrium. I was going to draw a graph of that. So if we had the amounts over here and time here, so we're going to going to draw our graph. We've got lots of A. There's A up there. A is going to react pretty quickly, but as the reaction goes on, it'll react less and less. Meanwhile, B, well, we don't have any B at the start because it's a product. The amount of B will go up, and then again, sooner or later, the reaction won't stop, of course. The reaction never stops. A is always making B and B is always making A. But we'll reach a point around about here where equilibrium's been reached, where the amounts of A and the amounts of B no longer change. Just want to be really clear about that. They remain constant. We'll say concentrations of reactants and products remain constant. So that's different, right? That's different from equal. You can see clearly on my graph here, A and B aren't equal. I've got loads more B than A. But they're remaining constant over time. If I went out and made a cup of tea and came back half an hour later, the amount of A and the amount of B wouldn't have changed. But the reactions are always continuing. A is still reacting to make B and B is still reacting to make A. It's just that they're reacting at the same speed and that's cancelling everything out. So we call that a dynamic equilibrium. Okay, static equilibrium is when everything stays still. If you stand up straight and don't move, you're in a state of static equilibrium. Your feet stay on the ground, you're not falling through the floor, you're not flying up into space, you're in a state of static equilibrium. All the forces cancel out. Dynamic equilibrium is where the reaction carries on, but there's no overall change. So reactants and products remain constant. Okay, let's just make a quick list of factors that affect. Let's do rate first, because we didn't actually make a list of factors that affect rate. 5 factors affect rate, just write them down for me. A list of 5 things? Got a list of 5 things? All 5? Okay. So we've got, do you want to start us off? Pressure. Area, and the missing one is? Okay, worth noting, just before we move on, that pressure can only affect reactions that are gas. And surface area can only affect reactions that have solid. And concentration can only affect reactions that are in liquid. Solution is more precise way, but yeah, they have to be. We can't have the concentration of a solid or the pressure of a liquid. Okay. Factors that affect equilibrium.
Pressure.
Definitely.
Temperature.
Okay, but that's it. Pressure, temperature, and concentration all affect equilibrium as well. But catalysts and surface area don't. As far as we're concerned, we're only going to look at equilibrium where everything in the reaction's a gas or everything in the reaction is a solution. We're not going to look at mixed, something that has a solid and a solution that reacts to make a gas. We're not going to look at anything like that. So we're simplifying things a little bit. Either everything's a gas or everything's in solution. Solids don't affect equilibrium anyway. That's because if you change the amount of solid, you've got all of that stuff which is kind of inside the solid, which can't affect the equilibrium because it's not reacting. Catalysts don't affect equilibrium. Anyone tell me why?
They only affect the activation energy.
They do affect the activation energy, but why doesn't that affect equilibrium? Because surely activation energy affects rate.
The same for both.
It's
The same for both.
It's the same for both. So catalysts will increase the rate of the forward reaction and the rate of the reverse reaction, and it does so equally. So if the forward reaction goes up by 10%, the reverse reaction will go up by 10%, and then they cancel out. So catalysts have an equal effect on both the forward and the reverse reaction. Okay. How are we doing? We've got a little bit of time. Right. So these things only affect our equilibrium. We've got a thing here. Oh, that was that. I was going to ask you what Le Chatelier's principle was. There it was. And then it's gone now. What was Le Chatelier's principle? How does temperature affect equilibrium? How does pressure affect equilibrium?
Well, it will go in the opposite direction to counteract or to minimise the change.
Counteract, minimise is a very good term. You remember that from last year? So it's that idea that if you go out on a cold day and you put on your big coat, but then it warms up later in the day as you're warming up, you want to minimise that change. You take your coat off to cool yourself back down to keep your body temperature within certain limits. So reactions, weirdly, without taking off coats, manage to do the same thing. The reason is, of course, that reaction doesn't have agency. It's not like it thinks to itself, oh, I must cool myself down. It's just that the change in temperature or pressure or concentration is affecting the rates of the reactions, which then affects the outcome. But I just want to be very clear about terminology that we use. If I'm talking about rate, then I want to be talking about rate, not equilibria. And because that would be very confusing, wouldn't it? If we said, if we asked a question about equilibria, but then used the term rate in it, because they're different effects and they affect the reaction in different ways. So rather than talking about rate, we're going to talk about equilibrium yield.
Would you say the equilibrium shifts so that there's
Yeah, we will say shifts, but we'll talk about the overall effects on the equilibrium yield. So you remember yield, right? It's the percentage of product that you make, and you can have 100% yield if everything goes perfectly, but more often than not, we lose a bit along the way. Well, for an equilibrium, we're never going to make 100% product. And if we make 90%, we're doing really well. If we're making 10% product, it's pretty rubbish for the reaction, whatever we're trying to make, paracetamol or whatever it is. So we want our yield to be as high as possible. So we want to maximize the conditions that give us a high yield. So I'm going to talk about rate. I'm just going to be talking about rate and collision theory and maximal Boltzmann distributions and activation energy and all that jazz. I'm going to leave that over there. Equilibrium yield is a completely different, not completely different topic, it's a different area. We try not to confuse the two. And I'm stressing that just because I'll often get questions like, how does an increase in temperature affect the equilibrium yield of ammonia? And then somebody will say, well, it'll speed the reaction up because the particles have got more energy. And it's like, no, that's not going to fly because the question's not about rate. That makes sense? Hope some of that made sense. I'll return to it severally. Okay. There we are. There's Le Chatelier's principle. Le Chatelier's principle states reactions in a state of dynamic equilibrium shift their position for a change to the conditions which minimizes the change. That's really the last three words that we need to have remembered. Any change to the conditions will shift the position of the equilibrium to minimize the change. Probably get through a bit of this now. Okay, so the example that you might remember from GCSE, and it's a good example because it's a real life example. Ammonia has to be made in large quantities. Can anyone remember from the GCSE why we need ammonia in large quantities? Yeah, we need to feed quite a lot of people on the planet, and we do that by using fertilizers. And the main fertilizer we use is not ammonia, but ammonium compounds, ammonium nitrate or potassium nitrate, things like that. So, or phosphates and sulfates. But you'll remember all of that stuff. So ammonia is very useful. We need thousands of tons of it a year. So we want to maximise the yield of the ammonia as far as possible. So the Haber process works at about a temperature of 450 degrees, which is obviously quite a lot higher than the temperature in here right now. And one of those reasons is we want the rate of reaction to be as fast as possible, and 450 degrees is definitely going to speed up the rate. So that's one thing, but we'll leave that over there now. How does a higher temperature affect equilibrium yield?
Well, it'll decrease the yield.
It will.
Shift it to the endothermic direction.
Okay. How does that affect the yield? Just deal with that first.
Decrease.
Yeah, that's going to decrease our yield. Having a high temperature. That's not so flash then. Okay, we'll come back to why we do it in a minute. Let's just first of all sort out the science. Why does a higher temperature decrease equilibrium yield? Yes, go on.
Shift the equilibrium position to the endothermic direction to offset the increase in temperature.
Okay, and I do have this on the next screen. Yeah, so Le Chatelier is all about minimizing change. It's kind of about undoing the changes that you've made. If we increase the temperature, the equilibrium will try and undo that. Well, how do you bring temperature down, or how do you absorb that extra energy? Well, that will be an endothermic reaction. Endothermic reactions absorb energy. Well, in this case, the endothermic is the reverse reaction. It's exo in the forwards direction to the tune of minus 92 kilojoules per mole. So it'll be endo in the reverse reaction. So the endothermic reaction will absorb the additional energy, which means the endothermic reaction gets a boost and we make less ammonia, which is not that great. Okay, so in kind of exam terms, what you need to say is that the increase in temperature or the increase in energy shifts the equilibrium in the endothermic direction. And can you please avoid trotting out the words minimize the change every time? You've got those in your head. You know Le Chatelier is about minimizing change. But then ask yourself, what change and how does it minimize it? Well, the change is the additional energy, and it minimizes it by reducing the additional energy. So that's my minimize the change statement. But I'm not going to get away with just writing minimize the change, minimize the change, minimize the change. That's GCSE for us. At A level, you're expected to be able to identify the change and how it's minimized.
Can I say this all, please, sir?
Of course you can. Okay, so if a reaction's exothermic, releases heat energy when it's going forwards. If we increase the temperature, equilibrium will shift kind of against us. It's undoing what we want. And this presents a problem to us. It means that increasing the temperature gives us a faster rate, which we want, but it also decreases the yield, which we don't want. So why 450 degrees? It's a compromise, yeah. It's a compromise temperature. It's like a sweet spot. If we go higher than 450, we won't make enough ammonia. The yield will be too low. If we go lower than 450 degrees, the rate will be too slow. So 450 degrees is a compromise between rate and yield. They're working against each other. So 450 degrees, yeah, it does say that is a compromise between rate and yield. Chemical engineers are always having to make compromises. You want to get the conditions just right so you're making as much ammonia as possible. So they would tinker with those conditions, you know, try 460 degrees, try 440. Look how much ammonia they're making on a particular day, and they want to maximize that amount. Okay. Temperature. All right. What about pressure? How does pressure affect an equilibrium? And more importantly, how does pressure affect this equilibrium? I'll just make a... Oh no, it's already here, isn't it? This is a general statement. Notice that an increase in temperature causes the equilibrium position to shift in the endothermic direction is always going to be true. Increase in temperature shifts the equilibrium in the endothermic direction is always going to be true. Similarly, a decrease in temperature will shift the equilibrium in the exothermic direction. That's always going to be true. So that's your guiding principle, if you like. Increase in temperature shifts equilibrium position, which is a direction, is a way of visualizing reactions, whether we're a long way towards the products or a long way towards the reactants. That's the reaction, the equilibrium position. So if we shift to the right, we're shifting towards the products. Okay, so if that's our guiding principle for temperature, what's our guiding principle for pressure? What are you going to take into the exam in your heads as your, as I say, your guiding principle that you're going to use to analyse exam questions? Can you remember pressure? Pressure. Under pressure. Go on, Josh.
An increase in pressure, the equilibrium shifts to the side with the least amount of
Okay, least moles of gas. Increase in pressure shifts the equilibrium position. I'm going to go with fewer. Is that all right?
So, the toilet, please.
Of course, yeah. Increase in pressure shifts the equilibrium to the side with fewer moles of gas. Again, that's your guiding principle. Given a reaction equation, how do we identify fewer moles of gas? Should probably just say these are all gases at room temperature. I'm sure you knew that. Let's turn things up. Go on.
Just count the numbers in front of you.
Yeah, we just count the big numbers in front of them, what's called the stoichiometry of the equation. There's a nice fat word for you today. Stoichiometry is just the posh word for balancing numbers. So we look at the balancing numbers, and what that tells us is that one nitrogen reacts with 3 hydrogens to make 2 ammonias. Seems like it might be impossible. So 1 plus 3 makes 2. How can that be? But it's because ammonia molecules are bigger, they've got 4 atoms in, than nitrogen and hydrogen molecules, which only have 2 atoms in. So we're making bigger molecules. And you remember that a mole of gas always takes up about the same amount of space, regardless of what the gas is. Do you remember how much space
24
a mole of gas is? 24?
dm.
Yeah, about 24 dm cubed at room temperature and pressure. So if I had a mole of nitrogen and 3 moles of hydrogen, that would take up 4 moles of gas, 4 lots of 24 dm cubed. But if I had 2 moles of ammonia, it would take up half the volume. It takes up half the volume, takes up less space. So if I squeeze my gas, if I increase the pressure by squeezing it into a smaller space, the equilibrium responds by minimizing the change. It wants to stop that increase in pressure, so it makes itself smaller, makes itself into more ammonia, fewer moles of gas, which is magic for chemical engineers, right? Because we already know an increase in pressure increases the rate, and for the Haber process, an increase in pressure increases equilibrium yield as well. So it's win-win. So what pressure do we use in the Haber process? Go on.
So 100 atmospheres.
100 atmospheres. Why don't we use 200 atmospheres? 300 atmospheres, 409,000 atmospheres. Why? Because we've just said, right, there's no compromise here between rate and yield. High temperature, we had to compromise, but high pressure gives us rate and yield that we want.
It's too expensive and dangerous to maintain.
Okay. Costs a lot of money in terms of energy, yeah, as a factor.
It's dangerous.
Dangerous. So we'd have to employ lots more safety procedures to make sure that our workforce didn't, explode and all die. They might have to have better training as well because they're working in conditions which are more dangerous. So they've got to, we're going to have to train them more. That always costs money. What else will cost more money?
The equipment.
Yeah, the containers we're using and all the pipes and the valves and all of that is going to have to be really strong to deal with those higher pressures. So we're still going to get to a compromise, right? We're not compromising between rate and yield now. We're compromising between rate and yield on one side, which are better the higher the pressure we use, and the cost of energy and containers and training and safety and all of those things. So we still have a sweet spot. We still have a compromise. Okay. So increase in pressure shifts the equilibrium to the right because there are fewer moles of gas on the right, increases the yield of ammonia and also increases the rate. However, a pressure above 200 atmospheres is not normally used because of high costs to energy, equipment and safety. Just a note, never just say cost in an exam. You'll never get a mark for saying it's expensive. You'll get a mark for saying it's expensive because of energy or whatever it is.